Welcome to Algebra 3. Welcome to February. We've had Groundhog Day. Uh, 6 more weeks of winter. Yeah, it's kind of that's what most of the years are because, winter is like another 6, 7 weeks away. So what a coincidence, right? Yesterday is also my wife's birthday. She's a teacher. So her birthday is Groundhog Day. And she did see her shadow. So 6 more weeks of homework. But yeah, that's good. Let's get our class pulled up here. Oh, the blinky. It'll quit when I click on the grade screen here. Let's go to the grade screen. See, we are through geometric series. All we have left is graphing sequences and series this week. And then next week is the exam. So next week we'll be having a practice test. So you can go and see what you know and what you need to review. And then the test part 1 to part 2. So we're almost to the end of our first module here. We've been taking it easy. And a lot of times we have 2 lessons a week, but we've only been doing one this getting this started back in January. Kind of needed the break. And I haven't looked at next unit yet, but I think we'll probably start picking up speed again. We got a lot to cover before the end of the semester, especially since you guys are seniors. All right, Coop. Since you guys are seniors and you don't go all the way the whole school year, right? Seniors will be done by like the second week of May. Woohoo! Yay. So since this class full of seniors, we want to get through all of our stuff and get done as quick as we can. So 5.08 this week. Take a look. I've got Desmos open. Since this is a graphing lesson, I would expect we will need Desmos as we compare some of these graphs. Information at your fingertips. In today's always online world, boy, isn't that true? News and data travel faster than ever. Information has become increasingly valuable. It's important to be able to decipher and communicate data in various formats. So infographics fill the internet because display data graphically can help others see the patterns, connections, and the big picture. So graphs, man, there's graphs everywhere on the internet, in business. It's a huge part of business, being able to look at graphs and understanding that. So graphing a sequence or series can also serve the same purpose. So for this lesson, what key features are unique to graphs of sequences and series, and how can the average rate of change be found using a discrete graph? So let's go to page 2 and see what it says here. A look at restrictions. That's always a key thing. When you learned about arithmetic and geometric sequences and series over the past 4 weeks, we've learned about how the domains have specific restrictions. Remember what the restrictions are on the domain? The domain is like the X, which is like the term number, right? The term number is the domain. And so it is all integers greater than or equal to 1, right? Because we cannot have a 0th term. We cannot have a 2.4 term of a sequence. We can't have any negative 3rd term of a sequence. So only natural numbers, 1, 2, 3, et cetera, are used in creating order. Decimals, fractions, and negative numbers are not included in the domain. Even 0, because we can't have a 0th place term. So very simple. On the range, it just depends on the sequence. It really has little to no restrictions. It could be a negative sequence. It could be a sequence that has fractions or decimals. It could be a fraction that goes forever. So it really just depends on the actual situation of the sequence you're using. Like if the range represented the number of ostrich eggs, then it would be restricted to positive integers or 0, right? You wouldn't be able to have negative 23.27 ostrich eggs. So restrictions on the domain is 1, 2, 3, 4 integers. On the range, it just depends on what sequence that you're actually looking at. So, and discrete versus continuous. Due to the limits on the domain, graphs of sequences and series are called discrete. That means they only exist at specific values. We don't connect them with a line because that's continuous. A line means every value between 1 and 2. If we have a line that goes from 1 to 2, we're talking about every single value between there is included And that's not true with sequences and series. So if we take a look, this is a discrete graph on the left, and on the right is a continuous one. So the one on the right includes every single number on that line, which includes all the decimals and the fractions, and it goes negative and everything. But the discrete graph, it only includes the points. There's no values included between the points. The first term is 2. The second term is 3. The third term is 4. The fourth term is 5. There is no term that's 4.5, or there's 1.5 term or anything like that. So we have to use a discrete graph. So using technology, we got to be able to understand how to do that. So investigate whether the graphing program or calculator choice will accept a sequence. So absolutely. You can, if you're like, okay, I need to graph a sequence. Well, you can graph it as like a table. Is the easiest way to do it with Desmos. So the first term, second term, third term, fourth term, fifth term. If the first term is 2, and the second term is 4, and then 8, and then 16, and 32, it's easy to put it in Desmos. And look, this is a discrete graph. See, it just does the points. And you can enter it very simply as a table. First term, second term, third term, fourth term. So we can do that in Desmos rather simply, and it will graph it correctly. So, but you could also just graph, if you want to, as a point, 1, 2, but then you're having to do the parentheses and each point individually, 3, 3,8. See, that works as well. Do it this way and labeling them. You know, you can do it as individual points, but it's a lot easier just to make the table and let it graph it as a table there. So very, very simple in Desmos. Average rate of change. The average rate of change can be calculated in the same manner it's been done for all other functions. Use the slope formula between the points. Average rate of change means the slope. So if we have this sequence, a sub n equals 5 to the 2n minus 1, find the average rate of change from n equals 2 and n equals 4. We can do it by substituting 2n for the n and 4n for the n and find what those values equal. So when you substitute 2, it's 2 to the 2 minus 1 power, or 2 to the first power, which is just 2. So 5 times 2 is 10. If it's 4, 4 minus 1 is 3. So 2 to the third power is 8. So 5 times 8 is 40. If you wanted to do that on a graph, 5 to the 2n minus 1. So we do y equals 5 times 2. And we would do x minus 1 on a graph since we have x's on here. Oh, I got to put it in parentheses. All right, let's see. If we did n minus 1, it would also work. You could do it as n minus 1. But on this, you would just have to zoom in and figure out what it equals at 2 and 4. Where is 2? 2 is right up here. 210. 210 is the point. So we can graph that point. And at 4, it's way up here. Oh yeah, 440. 440 is in the graph, so let's graph that point. And then on a graph, you can do rise over run, right? How much does it rise? From 10 to 40. It goes up plus 30. And how much does it run? It runs from 2 to 4. So it's 30 over 2. So the slope, the average rate of change is 15. Because 30 over 2 is a fraction. 30 divided by 2 is 15. Now, mathematically, we use this slope formula. We subtract the y's, subtract the x's. Same thing. 40 minus 10 is 30. 4 minus 2 is 2. That's the rise over the run. Slope is 15. That is the average rate of change. And in an arithmetic sequence, the average rate of change is equal to the common difference. As an arithmetic sequence, it automatically goes up. Here, let's do an arithmetic sequence. We can see, we'll do it as a table. First term, second term, third term, fourth term. So if we do 3, 6, 9, 12, common difference is 3 plus 3 each time. Well, that is also the slope because it goes up 3 over 1, up 3 over 1, up 3 over 1. With arithmetic, the average rate of change is just equal to the common difference. D equals 3. So that's very simple to find the average rate of change for arithmetic. Page 3. Okay, we're going to look at this video, see how long it is. It is 3 minutes and 7 seconds.
Let's take a look at graphing of series. Now, this is going to be a little different from what we're used to with just regular graphs, because a lot of times we'll come up with some data points, and then the first thing we want to do is go play connect the dots and draw a line through all of our points. But that only works when we have a continuous function. That is where there's some function at every value of our independent variable. But in the case of a series, that doesn't happen. For instance, my first graph here represents graduation from a high school. And they're having a little bit of population growth. So initially in year 0, their population, or year 1 rather, their graduation is going to be 500 students. But now between now and next May or June, there's not going to be any students graduating. So to connect the dots between year 1 and year 2 would be meaningless. So we don't connect them. We just graph them as discrete dots. The next year, it's gone up by 10, and then 10 the next year, and 10 the next year. So we can see that this is increasing linearly, and we have a series of dots here that form a straight line. But again, we do not connect with the line, but we can still see that it's a linear pattern. Now let's look at a geometric series. This is one that is increasing geometrically. We've got an R value of 1.5, and so each term is 1.5 times as great as the term before. And again, we are not connecting the dots here, but we can just see that it's beginning to grow rapidly or exponentially, we would say. Now we have a decreasing geometric series. In this case, we've got an R of 1/2. So since it's between 1 and -1, our terms are actually growing smaller, and as a matter of fact, they're going to begin to approach 0. And that's what we see here. Each time our values cut in half, and again, just discrete dots, no line connecting them, and we can see that this is falling off rapidly because we have a pretty small R value. And then one other case we might see is this is with a negative R, and we forgot our negative sign right here. Okay? And in the case of a negative R, what we'll see is an alternating series where one number is positive and then the next number is negative, and then the next number is positive and the next number is negative. And this one would actually represent, for instance, the maximum height that a swing would reach on either side. But in the case where, just due to the friction in the swing and the chain and whatnot, it's only going to about 9/10 the height that it did before. So each swing is only 90% of the previous swing. And so, yeah, it's going in a positive direction here, but now it's going in a negative direction here, but only 90% as far as this was, and then back to positive, negative, positive, negative, positive, negative. And this might model the behavior of a swing very well. And again, though, maximum height only occurs at the end of each swing. So once again, just discrete dots, no connecting lines. And these are just a few examples that we might see in the graphing of arithmetic and geometric series.
All right, there's a nice sample look at several of them then. So we see arithmetic up here. We've got what decreasing one. I like the positive and negative one that's shown over in the bottom right. That's a good example because we've seen some of those sequences that some of them are positive, then negative, and positive, negative. So it's good to see a graph of that. Let's look at these two examples. Here's the first one. Bart has been keeping track of people who say they're coming to his birthday party next week. Yay, he got 3 replies on the first day. And since then, he's gotten 5 more responses than the day before. So we got 3 the first day, then he got 8 the second day, 13 the day after that. So create an explicit equation that determines the number of responses he got, A sub n, and graph it. So this is identified as an arithmetic sequence because he gets 5 more each day than he received the day before. It doesn't say 5 times as many. See, that's geometric. Or 1/5 as many. It's a common difference, 5 more, plus 5. So it'd be a sub n equals a sub 1 plus d to the n minus 1 is our arithmetic sequence formula. So we got to substitute what we know in there. The first one was 3. That was the first day. He got 3 replies, and then 5 more each day. So if we take 3 plus 5, n minus 1, if we distribute that, that's 5n minus 5. So our formula, 3 minus 5 is minus 2. We can graph this right here, 5n minus 2. So this a sub n equals 5n minus 2. We go to Desmos. Y equals 5n minus 2. Now it's going to graph it as a continuous. But we do have options here. If we go to the settings and say make a table, it's making a table of that as well. Let's see if I take off that. Now I took off the original equation up there and just left the table. But let's delete the negative terms. We don't have a negative 2 term and 0 term, none of that. And we just leave the positive terms. So it graphs those for us. But look, if we want to add terms, it's going to automatically calculate for us. 3rd term, 4th term, 5th term, 6th term. It's automatically calculating what those terms will be since I created a table based on this equation. So look, I can graph the first 6 terms in Desmos, going to the settings and making it a table. And just delete the negative 2. We don't need the negative 2, don't need the 0 term. Just start with 1 and go upwards, and you can create a nice graph rather simply. We didn't have to do a whole lot other than enter what the equation is. And it made a 9-element list now because it's still counting those there. So we can graph that pretty nicely. So there is the graph. Well, ours is looking steeper just because of how we've got it set up. They've spread theirs out like this. They've said x is negative 10 to 10, right? So step one, take off the minors. See how that looks. Then we go to 10. We can cut that down to 20 or something like that. Make it as steep as you want, depending on the scale of you want to do things there. Because they're doing 0 to 8 and 0 to 45. But the point is, you don't want a line connecting those. You do not want a line connecting those. Graph of the Jew. Oh, let's look at example 2. I just did example 1. Maddie took some stale bread down to the pond to feed the ducks. On the first day, there was 4 ducks. The news spread throughout the duck community. The next day, there were 11 ducks. And then there were 18 ducks. She's gotten concerned she's not going to have enough bread. So let's graph the sequence for the first 8 terms. So yeah, I'm going to get some paper out. Let's figure out how to graph this, because we need to write an equation that would work for that. So if we look back at our first one, they used the a sub n. I will launch my camera here. I'll write this down. All right, and it said on the first day, a sub 1, there was 4 ducks, and then there was 7 more ducks each time. So our common difference is D, right? Because it didn't say there were 7 more each time. It actually said that, oh, where's example 2? That the next day there was 11 ducks, and then there was 18 ducks. So we can see that each time it's plus 7. So if our common difference is 7, and we need to make a formula, a sub n equals 4 plus distribute that, 7n minus 7. Now we got 4 minus 7. So this equals 7n minus 3. That is a linear equation that will represent that. So we can go to our Desmos screen. Get rid of this original one here. And make this 7n minus 3. Okay. let's see, I'm going to change. No, I'll leave that scale. That's okay. If we go to our settings and make a table, and again, let's delete the negative values. We don't have a negative term. We don't have a zero term. And we want to add, it said through the 8th, 6, 7, 8. So here is the first 8 terms. Click on them, it'll show you the values of the first 8 terms. So on the 8th day, she's going to have 53 ducks if word keeps spreading through the duck community like that. First 8 terms. And then we made a nice table for it right here. So that made it very simple in Desmos to be able to graph that. Just changing it to a table again. Go to those settings and make it a table. And then delete the negative terms, the zero term, because we don't have those. Remember, we start with 1. And you can add as many terms as you like, and it'll graph it real nicely there on Desmos for you. So check our work. There it is, from 1 to 8, and 8 is at 53. There's the 50. So ours was 53 right there. But there is the graph, 7n minus 3. So just take that equation and substitute and then simplify. And you could do it at a plus 7n minus 1, but good gracious, simplify that. Make it easier on yourself. And that is a discrete graph of that sequence. All right, let's look at geometric. So geometric is using a sub n equals a sub 1 times r n minus 1. N minus 1, I'll put parentheses up there. So Wyatt earned 80 points on a recent project. So his instructor allows to earn 1/10 of the points earned by doing some revisions. So he can revise that and earn another 10th. And he can resubmit his project 9 times. Each time he can earn an extra 1/10 of the points that he earned on the submission before. So let's create an explicit equation that determines the points on each submission he earns and then graph it. So a sub n geometric sequence gets 1/10 of the points. So let's substitute what's in. His first time he got 80 points. And he can get 0.1 points each time, n minus 1. So let's graph that, 80.1 n minus 1. All right, get rid of these. Equals 80 times 0.1 raised to the power of n minus 1. I put n minus 1 in parentheses, so it makes it all of that an exponent. And here is our starting graph. What's it wanting? For 9 submissions, that would say he can resubmit his project 9 times. So let's change this to a table. Get rid of the negative values. Take this up to the 9th value. 3, 4, 5, 6, 7, 8, 9. Now let's uncheck the continuous up there and just leave out the settings and just leave the table. So our first one is at 80. Then he can get 8 more points the second time. He can get 0.8 points the third time. He can get 0.08 the fourth time. 0.008, 0.0008. If we keep submitting this, now it's down to, oh, it thinks it's a 0. I wonder if we zoom in, if it'll change that to not a 0. It should just be a whole bunch. Oh, now it's at a 1. There it is, 0.000008. So when he's done, he can have 88.8888888 points. If you add all those points together that he's getting on top of that. So let's back out of this. That is our graph that we made all the way up to the 80. There we go. Our graph that we made all the way to the top there. When they put it into the graphing software, there's what it looks like. Oop, that's exactly what ours looks like. Right there. All right, page 4. So graphing and arithmetic are geometric series. Oh, so let's I'm gonna put this in our notes. So this was the arithmetic sequence formula that we had to use to graph the arithmetic sequence. When we had a geometric sequence, we use this. This was arithmetic series and geometric series. So these are the starting formulas that we need. And then we have to substitute whatever information we have into that. There, I got all 4 of them on the screen. So make sure, those should be in your notes from the past 4 weeks, but I'm just bringing them all in one place right here, that we can have them all together for this graphing lesson, I'll give you a moment if you're writing those down to have those in your notes. Again, you may have your old notes from the last 4 weeks and have them all organized already. But if you want them all in one place, we've got these right here. These are the ones that we're using for graphing. We're just substituting numbers in here. And again, these are in our lesson right here as well on page 4. Might be easier to read it off page 4. But remember, the sequence is the sum, with the series is the sum, so we have the S sub n instead of A sub n. So let's look at an example using the series formula. So Bart has been keeping track of the people who say they're coming to his birthday party. Got 3 replies. Oh, wait, we looked at this. Oh, but we didn't look at the total. We looked at each day. 3 replies first day, and since he's got 5 more, create a sum formula to know how many he gets altogether. But it doesn't say how many days. Oh, just the sum formula. So the sum formula, we're going to use the arithmetic sequence that we got there. So he got 3 the first day. So A sub 1 is 3. And his common difference was 5 more each day. So taking this, S sub n would be n divided by 2, 2 times A sub 1. 2 times 3, 2 times A sub 1, plus 5 n minus 1. Okay, let's simplify what we can here. N divided by 2 times 6 plus 5n minus 5, right? When we distribute 5 times n minus 1. So this is n divided by 2 times 5n, 6 minus 5. So we should be able to graph that. And then for however many days, it'll give us the total. So let's see what we do with that. N divided by 2, 5n plus 1. So let's graph that. Okay, let's get rid of this. So y equals n divided by 2. I'm going to put that in parentheses to keep that together. Times 5n plus 1. I'll put that in parentheses. All right, and let's make a table again, because we only want the series. We don't want the continuous. Let's uncheck the red box there. And let's add more terms. 3rd day, 4th day, 5th day, So he gets 3 the first day, 11 the second day, 24. Well, 11 is not the second day. That's the total because he gets 5 more, right? So he gets 8 the second day. That means he got 3 the first day plus 8 the second day. He's got 11 total. And then he gets 13 the next day. So that gives him 24 total. He's going to have a big party. So he's got 65 that he's received by day 5 total for the series. Oh, and they're continuing all the way up to 8 days. So let's go 8 days here. 6, 7, 8. So he's going to have 164 people coming to his party. If he receives replies for 8 days, and the last day, he got another 38 on the last day there. Big party. Okay, let's look at example 2 for this. This is the one where you got 80 points on a recent project. So we need a sum formula that'll do all of that together. All right, let's see if we can create that then. So he had A sub 1, he got 80 points originally. And it said he can get, how much did he get? 1/10 of the points. So R is 0.1, 1/10. So let's substitute in. S sub n equals 80 minus 80 times 0.1 to the n over 1 minus 0.1. So 80 minus 80 times 0.1 to the n. And this is 0.9 at the bottom. So let's see, did they combine that? I want to make sure I do it the same way they did it there. No, you have to leave that separately because we don't know what 0.1 to the n is until that's done.
Any other questions that have popped into your head to make it
You can only simplify the bottom as the 0.9 right there. So that has to stay separately because we don't know what n is, so that's going to change. 80 times whatever this is. So we can put this in and graph this. Just got to use parentheses to keep things where they're supposed to be. So let's do that. Get rid of that table. Get rid of that. Okay, so y equals.
There's no 100% answer. So
On top, we got 80 minus 80 times 0.1 raised to the power of n, close, well, not that, close parentheses. That's what's on top, divided by 0.9. Okay, so there's what the graph looks like, but we need a discrete graph, so we're going to go to the settings, create a table. We're going to get rid of the negative second term, the negative first term, and the 0th term, because those don't exist. We're going to turn off this continuous graph up here and create more terms. 4, 5, 6, 7, 8, 9. Remember, he could do it 9 times. 9 times he could submit. So if we go and see how many total points he will have on the 9th time, we'll get him more if we zoom in any more than that.
but it's going through, like right now, if you come to be
I think it's rounded it to the 9.
those cell phone signals are coming in.
Yeah, it's 88.88889 because it rounded it. Because it should go more 8s, I believe, if we keep going, but it's not going to let us zoom in that far. It's going to take a long time to get there, I guess.
Signals that are flying around. Like even
All right.
right now, think about all the signals flying around through your house. Your TV's plugged in.
Long ways in there. And there's the graph. They're showing the same thing. 80 points, then 88 points, then 88.8 points, then 88.88 points, and keep going. to see how many total points he can get. So you can get almost about an 89 for the assignment. Lesson summary. All right, there's our questions. How can an expression or process be determined for a geometric sequence? What functions combine to create an explicit formula for geometric sequences? What possible restrictions? So there's the restrictions, domain and range. Remember, discrete graphs, they're only valid at specific points. They are not continuous. Not continuous. So here's the formulas for graphing arithmetic sequences or geometric sequences. Here's what you use for arithmetic series or geometric series. And here's the slope formula to find slope between points. Great place for your notes for this lesson right there in the lesson summary. Gives you the formulas you need to use to be able to graph it. All right, let's look at these sample problems they have on page 5. So we have a good idea of what we're doing.
Don't go that extreme.
Graph the sequence. Check your result. All right, so we want to graph the first 6 terms of a sequence where a sub 1 is -3 and d equals 4. So we want to go back to this one.
Some of you can focus, lock in. Some of you need to watch it 10 times. And then the outbreak game.
There we go. Substitute what we know. -3 plus 4 n minus 1. -3 plus 4 n minus 4. So it equals 4 n minus 7 because we got -3 and -4. So let's graph that. The first 6 terms. All right. Getting rid of that. Getting rid of that. I wonder if we can do let's see, a sub n. A sub n. Yeah, you can do a sub equals 4n minus 7. Again, table, error creating table. Oh, because I guess it does have to have y to be able to do that. There we go. Now let's do a table.
1,400 people. 1,100.
Delete the negative terms, delete the 0 term, and then with the first 6 terms. Oh, wait, that should be 3, 4, 5, 6. There's the first 6 terms. Turn off the formula up top. Leave just the table. And there's what it looks like.
Okay. Your goal is to get 1,000.
Yeah, let's balance this out a little bit. Go from
You're playing it. You're going to
go to 15 on both graphs. Oops.
Each outbreak has 1,500 available.
Look a little more balanced.
So you could literally do one to get that 1,000 points and feel like I am so bad.
The first term, second term, third term,
Okay.
fourth term, fifth term, and sixth term. There's our 6 terms
1, 2, 3.
right there on the graph, and we have them here on the table. Check your work.
I need a screenshot.
There's the 6 terms, and they gave the values of them up top. The last one should be 617. 617. First one was 1, -3.
Your goal is 1,000 points.
All right, good job. Let's see, there's 6 practice problems.
Classroom in that order.
All right, let's give you a chance to see if you can do this. I want you to open Desmos. And let's practice this together. We'll see if you can get the same thing. Open Desmos. I'm gonna put my formula up on the screen. First, we'll see if you can just graph it based on the formula. Graph the first 6 terms of a sequence displayed in the table. So we have to first figure out what this is. First term, second term, third term, 14, 11, 8. So obviously this is arithmetic where the first term is 14 and the common difference must be -3. It's going down 3 each time. So I'll help you with this part on the first one. So we're using the same formula. 14 minus 3 n minus 1. The common difference is a negative 3. 14 minus 3 n plus 3, because negative 3 times negative 1. So negative 3n plus 17.
Minimum on that.
All right, I want to see if you can graph this as a discrete graph. So I did the formula for you on this first one. Go to Desmos and see if you can make a graph of that sequence. Here's your chance to practice while we're together. If you're having problems, I'll do this in a minute and you can compare to see, oh, what did I do wrong? I thought I knew how to graph this. Perhaps I don't. If you're having trouble, I'm going to do it in just a minute. I'm going to give you a chance to see if you can get the graph first. If you can make it a discrete graph, not continuous, remember, because we don't want to connect all the points because there's no values in between the points. Get rid of that. So we're graphing y equals negative 3n plus 17. So there's our start. Hopefully you got that much done. But this is not our final graph because this is continuous, right? This has all the values. So did you make it that far? Now were you able to convert it to where it's just a discrete sequence? Okay, you go to this settings. We're going to edit and create the table. Then you can turn that off if you want. I'll say done. I'm turning off this one when I unhighlight that. So now it's just got the points. But it has these negative terms. We don't have negative terms. I'm getting rid of those. And how many terms did we need? 6 terms. I've got 2 terms. 3, 4, 5, 6. It'll automatically calculate the rest of the terms for you. Just tell it how many you want. I want terms 3, 4, 5, and 6 added. It'll automatically calculate what those are because it knows the formula that we used, that we made that table from. And there is our graph of the first 6 terms of that geometric sequence. I'm sorry, that arithmetic sequence, not geometric. It's arithmetic sequence. All right, how'd you do? Did you know how to get from here to the table? Hit this little settings button up here, create table. Then you just have to modify the table.
Yes, ma'am.
Check your work. There you go. Same table. 6, negative 1 is our last term. That's what we had. 5, 2, 4, 5. 4, 5, 5, 2, 6. There we go. Let's look at this one. Let's try another one. We're about to look at our assignment here in just a minute. Graph the first 6 terms of a sequence where A1 equals negative 3 and R equals negative 2. R equals negative 2. So that means I need a geometric sequence because they want the first 6 terms. A1R n minus 1. A1 R n minus 1. Do y equals, because that's what I have to do on the graph. Negative 3, negative 2, n minus 1. Let's see. Y equals negative 3 times negative 2. That would actually graph at 6. Raised to the power of n minus 1. Oh, put that in parentheses. N minus 1. Why do I just have that 1 point? If I said x minus 1. So when n equals 2, well, there is a bunch of them there. Let's delete those, delete the 0. Let's do a third, fourth, and fifth term. Turn off that one. Oh, there they are now. I don't know why I didn't see it before. So this is one of those that's a negative, and the second term's positive, and the third term's negative, and the fourth term's positive, and the fifth term's negative, and the sixth term is positive. This is one of those diverging ones. It goes positive, negative, positive, negative, positive, negative. Let's see if that's what they got. Yeah. Positive, negative, positive, negative. It keeps going up and down, up and down, up and down. That is what they got. Okay. Mm-hmm. All right. And then they have first term's 100, second term's 90, third term's 81. That is not arithmetic because it subtracts 10, then it subtracts 9. So it looks like this is multiplying by 90%. So you got an R of 0.9 because 100 times 90% would be 90. 90.9% would be 81. Yep, 0.9. Fifth one, 6 terms of a series. A1 is 5, D is 2. And R is 2. Finite series. So, all right, let's look at our assignment. Calculate the average rate of change from n equals 2 to n equals 6. Well, where's n equals 2? It's right here. 14. When it's 6 is 2, you can do rise over run. How much does it rise? How much does it run? And simplify that fraction. It goes from 14 down to 2. Then it goes from 2 to 6. Calculate the average rate of change from n equals 1 to n equals 3. Here it is at 1. Here it is at 3. How much does it rise? How much does it run? This is at 2. It goes up to 8. And then goes over to 3. Graph the first 6 terms. A1 equals 3. D equals 10. So which one of these 4 graphs is the graph of this sequence? First 6 terms, A1 and R. So this is geometric. 6 terms. Which one of these is it? Again, you can graph it here and compare, right? Go make your own graph and see, is that what mine looked like? R equals 1.5. All right, 5 questions. So we got 5 questions. 5, 5, 5. So graphing, again, use Desmos. Desmos makes it so much easier because I've showed you several examples there of how you can graph that and make it work right. So, all right. If you got questions, hang around. Otherwise, you got about half an hour that you can work on this for your next class and probably have this done. There's only 5 questions. So it is an A-day Friday. So if your grade's below 70%, which this class, you guys don't have missing assignments. Make sure all your assignments are turned in and most of y'all have an A. I think all but 2 people in this class have an A right now. And those 2 people, I think, have missing assignments. So I'll be here Wednesday and Friday if you need me. Otherwise, I'll see you next week. Have a great one.